7.4 is on partial fractions. I'm going to show you what a partial fraction is before we start doing a partial fraction decomposition. So if you look at the top, I wrote that this fraction plus this fraction is equal to this fraction. So the two fractions that were added together, this one and this one, these are called the partial fractions. And they're just the little fractions that make up the entire rational expression. Okay, it is useful to break up like the sum of fractions into each little piece when you get to calculus, because it will be easier to work with each of these individual partial fractions rather than dealing with the entire sum at the same time. So we're practicing this totally randomly right now, but once you get to calculus, this will actually be useful. Okay, now the way you set it up kind of depends on the problem you have. Okay, so let me see. The first thing I'm going to do though is if I look at example 1, I'm going to factor the denominator so I can just kind of see probably what the two denominators were before they were added together. And you can do this in your head. I'm okay with that. Okay, but on the next, actually I would probably do it on the next step, but I'm going to do it there for now. So on the next step, I'm going to say that this fraction, which is the original fraction, I just factored it to make it clearer, should be equal to, in this case, it's going to be two fractions added together. Okay, one of the fractions is going to have a denominator of x minus 3, and the other fraction is going to have a denominator of x plus 2, because that's most likely how they created the common denominator of x minus 3 times x plus 2. I have no idea what the numerator for each of those partial fractions are, so that's actually what I'm going to solve for. But this is the setup with the constants. Okay, from here, I want to figure out what a and b are. So I'm going to solve this equation. Since this is a rational equation, I think I'm going to cancel out the common denominator. So I'm going to multiply the entire equation by x minus 3, x plus 2. Okay, if I do that, okay, for this first fraction, the x minus 3 and the x plus 2 both cancel. And then I'm left with 7x plus 4. Okay, now if I multiply this fraction times x minus 3 times x plus 2, the x minus 3's will cancel, but I will still be left with a times x plus 2 because the x plus 2 did not cancel. Okay, now I'm going to go to the next fraction. On this last fraction here, the x plus 2's cancel. I'm left with the b times x minus 3. Okay, now there's more than one way to solve for a and b. I'm going to use systems of equations to do it because it works in every case, whereas there's another strategy your book uses that works in certain cases and it doesn't work in other cases. But I'm going to distribute, even though this looks terrible. Okay, now I'm going to create a system of equations using the fact that the like terms on the left side must be equivalent to the like terms on the right side. Okay, so what am I saying? Okay, on the left side, I see this is a 7x. On the right side, I see an ax and a bx plus bx. Okay, so it must be true that 7x is equal to ax plus bx so that the like terms on the left side and the right side match up. If I divide both equations by x, or if I just consider only the coefficients, it would tell me that a plus b must equal 7, and that's because ax plus bx has to equal to 7x, so it must be true that if I add these coefficients, it must equal to 7. Okay, next I'm going to look at the constants. Okay, so for the constants I have, on this side I have a positive 4. Okay, on the right side I have a 2a and a minus 3b. So it must be true that 2a minus 3b equals to 4 because those are the constants added together. And now I have a system of equations, two unknowns. I'm going to solve for a and b, and then I'm going to rewrite my fraction. Okay, now whether you want to do substitution or elimination, they look equally accessible at this point. I think I'm going to use elimination, but it's up to you. Just show your work so I know what you did. Okay, I'm going to multiply by 3. So a is 5, and I'll plug it back in to get b into the a plus b equals 7 equation. So b equals 2. But I am trying to write this as a partial fraction decomposition, so I'm going to go back and see what my two fractions are. So I wrote it as a over x minus 3. So 5 over x minus 3 plus b over x plus 2. Okay, this is my partial fraction decomposition. If I wanted to check if I added these two fractions together, it should result in this fraction here. And even if you set this up oppositely, our final partial fraction decomposition should still match. Okay, now the next example is similar, but depending on the factors you have in the denominator, you set it up slightly differently. So in this case, it's going to have a quadratic factor, which I'm telling you it's going to have. You would have to notice it on your own. Okay, but I am going to first factor the denominator the best I can. So I can see what the denominators for each of the partial fractions will most likely be. Okay, so x cubed plus 9x has a common factor of x. If this would factor more, I would, but because it's a plus 9, it does not factor more. Okay, based on the factors I have here, most likely the denominator for one of the partial fractions is x, and the other one is x squared plus 9, which is very similar to the previous problem. Now for the numerator, I'm just giving it some random constant of a. Okay, now for the next one, since the denominator is x squared plus 9, it's possible that the numerator could have an x in it, or it could be a linear factor. So to keep this in mind, I have to say this is bx plus c. Okay, there might be an x here because the degree of the denominator is x squared, and this would still be a fraction that's not an improper fraction. So this is an allowable fraction. So if it's quadratic, we're doing something like bx plus c. If there was another quadratic factor out here, I would make it dx plus e, and the constants keep increasing that way. Okay. I'm going to solve it similarly. I'm going to go ahead and solve for a, b, and c actually. So let me multiply by the common denominator, which is the x, and the x squared plus 9. Okay, so for the left side of the equation, the x and the x squared plus 9 will both cancel. And I'm left with 5x squared plus 27 equals. Okay, now when I get to this fraction, the x cancels with the x, but I'm still left with the a and the x squared plus 9, which I'm going to write out. If you would like to distribute that in your head, you can, but still show your steps. Okay, now for the next one, let's see, the x squared plus 9 cancels with this, and I'm left with the bx plus c times the x. And make sure you put the bx plus c in parentheses so you don't forget to times the entire expression by x. Okay, now I'm going to go ahead and distribute it, and then I'm going to match up the like terms on the left and right so I can create my system of equations. And be really careful when you multiply this out, because that's often where the mistakes occur. Okay, now it doesn't matter which like term I start with. I'm going to start with the quadratic terms. So let's see, I have 5x squared, ax squared, and bx squared, which means that a plus b equals 5 because the coefficients on the right should match the coefficients on the left. Okay, let me go to the linear terms. Okay, so I have negative x or negative 1x. See what terms have an x. Just this thing over here. Actually, that's really nice. So since cx equals negative x, that must be true. It must be that c equals negative 1. So I already have the c value. Okay, let's look for the constant now. So I have 27 equals 9a. Okay. So even though this had more constants, it's actually going to be easier to solve because I can get a equals 3. I already know that c equals negative 1. And I can get b by using a plus b equals 5. And then I have to remember to go ahead and rewrite my partial fraction decomposition. Okay, so it does depend how you set it up when you rewrite it. So because I set it up like this, rather than switching the terms or anything else, I have to rewrite it the way I set it up. So I have a over x plus bx plus c over x squared plus 9. Okay, so this is my partial fraction decomposition. Of course, I could add these, find a common denominator to check my work, and it should be equivalent to this. But again, this is just easier to work with when you're doing certain things in calculus. Okay, the next scenario for the partial fraction decomposition is going to be when the denominator has repeated linear factors, which I'm going to show you. And I'm going to show you how to set that up. And then I'm going to show you how to set up a couple other scenarios, even though we're not going to do examples on every single one of them. Okay, so if I were to factor this denominator, I would take out the x. Okay, now because x squared minus 2x plus 1 factors more, I'm going to factor this even more. Okay, and I'm just doing this to figure out how to set up my partial fractions with the constants because I need the factors to know how to set it up. Okay, now the thing that makes this different than the previous examples is that the x minus 1 occurs twice. Okay, so let's start with the easy one. Okay, first off, what do we have? The first factor I'm going to use is x, and the order doesn't matter as long as you are consistent. Okay, now the next factor is x minus 1. Okay, now it would not make sense to write x minus 1 again, but I do need to keep in mind that there is an x minus 1 times x minus 1 down there. Okay, so because x minus 1 is a linear factor, I put a c at the top. But because I use the x minus 1 more than once, now I make a denominator of x minus 1 squared, because it's possible there's a fraction that has x minus 1 squared that cannot be written as b over x minus 1. If this was x minus 1 to the third, then I would add another one that said plus d over x minus 1 cubed. So however many times repeats, I keep including another partial fraction for that. Okay, now the solving of it, hopefully you're getting used to the solving. I'm going to multiply it by the least common denominator, x times x minus 1, x minus 1. The fraction cancels on the left, it always does. Okay, now when I get to this first fraction, the x's cancel. But keep in mind, I do have x minus 1 times x minus 1 left. Okay, now when I get to the next fraction, the x minus 1 cancels, one of them cancels, but I still have a b, x, and an x minus 1 as my remaining factors. Okay, and then for the last fraction, the x minus 1 squared cancels and I'm left with an x. Okay, so the hardest part of this one is actually the multiplying it out. Okay, now I need to multiply x minus 1 times x minus 1. You can do it on your head or you can FOIL it off to the side. But it's going to be x squared minus 1x, which is minus 2x, plus 1. You do need to multiply it all the way out or you're going to mess up on a term. It will be missing, your work will be crazy, and I will not know what's going on. Okay, so I'm going to now distribute the a. Okay, now I'm going to line up the like terms so I can get some equations here. So the quadratics a and b, so a plus b equals 3. Okay, let's see what else. For the negative 1x, I have negative 2ax and negative bx. Oh, nope, I lost my x at the end. Plus cx. That's why you got to be careful. That would have messed up my entire equation. Okay, so negative 2a minus b plus c equals negative 1. Okay, and then for my last one, I have the 5 equals just the a. So a equals 5. Okay, which is good because at least it gave me one of the answers. Okay, since I know a is 5, I'm going to plug that into a plus b equals 3. Okay, now I need c, so I'm going to have to plug it into the big equation. Minus negative 2. What is that? Negative 8. So c is 7. Okay, and then after all that, I still need to rewrite my actual fraction, my partial fraction decomposition. So I have a over x plus, what's b? b over x minus 1. I could have made that a minus 2. Plus c over x minus 1 squared. And again, if you wanted to re-add these up, you could do so to verify that they do in fact work. Okay, now I'm just going to list for 2 scenarios what it would look like, but I'm not actually going to solve it out because it's the same process as the other ones. Okay, let me make something up. 3x cubed plus x squared minus 5. I want a repeated quadratic factor. So how about x squared plus 3 squared? Okay, if I were just setting this up, because it's quadratic, I would have to use ax plus b for the factor x squared plus 3. And then because it's repeated, I then have to do a denominator of x squared plus 3 squared. And the numerator would still be linear, so I would call that cx plus d. And then I could solve for a, b, c, and d. And write the partial fraction decomposition that way. It is possible that a, b, c, or d, or one of the constants could be a 0, and that's fine. Okay, the second scenario I'm going to show you is sometimes you get a fraction for your constant, and there's nothing wrong with having a fraction for your constant. So for example, let's see, say I got a fraction for my constants. I'll show you 2 ways to write them. One would be to write maybe 3/7 over x plus 5 minus 2/7 over x minus 4. I'm okay with you writing like this. This isn't the nicest way to write it, but it's an okay way to write it. Often, WebAssign will factor the 1/7 out. So they'll make this 1/7 times 3 over x plus 5 minus 2 over x minus 4. And these are equivalent answers. I'm okay with you writing it either way, but just know they are the same. So if you see WebAssign's answer like this, it only occurred because they got a fraction for each of their constants.